In the second part of our lecture series on types of data science and machine learning models, we will delve deeper into the diverse landscape of algorithms and models that form the backbone of data science and machine learning. This session is designed to build upon the foundational concepts introduced in Part 1, guiding you through a more detailed exploration of various model types, their applications, and the theoretical underpinnings that enable them to extract valuable insights from data. We will begin by categorizing the models into broad types based on their purpose: supervised learning models, unsupervised learning models, and reinforcement learning models. Each category serves distinct objectives, from predicting outcomes based on input data to discovering hidden patterns and making decisions in dynamic environments. Following the categorization, we will focus on specific models within these categories, such as linear regression, decision trees, neural networks, clustering algorithms, and Q-learning. For each model, we will discuss its mechanics, where it excels, its limitations, and real-world applications. This discussion will not only enhance your theoretical knowledge, but also provide practical insights into choosing the right model for specific data science tasks. Additionally, we will touch upon advanced topics like ensemble methods, which combine multiple machine learning models to improve prediction accuracy, and deep learning, a subset of machine learning that uses neural networks with many layers to analyze complex data structures. Throughout this lecture, we aim to equip you with a comprehensive understanding of the various data science and machine learning models, fostering your ability to apply these concepts effectively in your projects or research. Whether you are a budding data scientist, a seasoned professional looking to refresh your knowledge, or someone with a keen interest in the field, this lecture will offer valuable insights and deepen your appreciation for the intricate world of data science and machine learning. Supervised machine learning is akin to a guided learning process, where we aim to predict the value of a target variable based on a set of input data. This form involves training a model on a dataset that includes both the inputs and the desired outputs. The two main tasks under this umbrella are classification. This task focuses on predicting which category, class, or label an unseen instance belongs to. An example provided was transaction fraud detection, classifying transactions into categories like low, medium, or high risk. Regression. This task predicts a continuous quantity, answering questions of how much or how many. It's about estimating a numeric value based on inputs like forecasting sales volume. Ensemble models, though briefly mentioned, are essentially a blend of multiple models aiming to improve predictions through techniques like bagging, boosting, or stacking. Transitioning to unsupervised machine learning, this approach deals with data without predefined labels or outcomes. The aim is to discover hidden patterns or structures within the data. Key tasks include clustering, grouping data points based on similarity, such as segmenting customers with alike behaviors. Dimensionality reduction, simplifying the dataset by reducing the number of variables, focusing on the most informative features. In addition to supervised and unsupervised learning, the lecture introduces imputation and time series analysis, special cases of supervised learning, dealing with missing data and analyzing data over time, respectively. Reinforcement learning, a method where agents learn to make decisions by interacting with an environment, aim at maximizing some notion of cumulative reward. Neural networks and deep learning. Inspired by the human brain, these models use layers of nodes to process data and make complex decisions. Monte Carlo simulations, rule-based models, and statistical approaches like A/B testing are also highlighted as essential tools within data science, showcasing the field's diverse methodologies beyond the traditional machine learning paradigms. The lecture emphasizes the significance of model evaluation, especially from a business leadership perspective. Understanding model objectives, limitations, and evaluation metrics is crucial for aligning business and technical teams. This alignment ensures the development of models that not only meet technical specifications but also deliver tangible business value. Model evaluation revolves around understanding the trade-offs between model complexity and performance, the costs associated with false positives and negatives, and the importance of setting realistic performance goals. It underlines that in data science, perfection is often unattainable without prohibitive costs, urging a balanced approach to resource allocation and goal setting. Expanding on machine learning types, semi-supervised learning occupies the middle ground between supervised and unsupervised learning. It uses a small amount of labeled data alongside a large pool of unlabeled data to improve learning accuracy. This approach is especially useful when labeling data is expensive or time-consuming. Self-supervised learning, a subset of unsupervised learning methods where the model generates its own supervisory signal from the input data. This innovative approach is gaining traction for its ability to learn rich representations of data without explicit labels, proving valuable in fields like natural language processing and computer vision. Going beyond basic models, Generative Adversarial Networks, GANs. These are deep neural architectures comprising two networks, a generator and a discriminator, which are trained simultaneously through adversarial processes. GANs are renowned for their ability to generate new data instances that resemble the training data, useful in applications like image generation, style transfer, and more. Explainable AI, XAI. As machine learning models, especially deep learning, become more complex, the demand for transparency and understandability increases. XAI aims to make the outcomes of AI models more interpretable and trustworthy, a critical aspect for applications in regulated industries like finance and healthcare. Integration with business processes, operationalizing machine learning. Moving beyond model development, it's important to consider how models are deployed and integrated into business processes. This includes model monitoring, updating models with new data, and ensuring models remain accurate and relevant over time. Ethical AI and bias mitigation. Businesses must also address the ethical implications of machine learning, ensuring that models do not perpetuate biases or make unfair decisions. This involves careful data curation, model testing for bias, and implementing fairness algorithms. Strategic implementation and leadership. Data strategy alignment. For machine learning projects to deliver value, it must be aligned with the organization's data strategy. This includes data governance, quality, and architecture considerations, ensuring that the necessary data infrastructure supports ML initiatives. Cross-functional collaboration. Effective machine learning projects require collaboration across data scientists, business analysts, AI professionals, and decision-makers. Establishing cross-functional teams helps ensure that models are not only technically sound, but also address key business challenges and opportunities. Continuous learning and adaptation. The landscape of machine learning and AI is rapidly evolving. Organizations and their leaders must foster a culture of continuous learning and innovation, staying abreast of emerging technologies and methodologies to maintain competitive advantage. In summary, this lecture underscores the importance of a holistic understanding of machine learning and model evaluation. By bridging technical and business perspectives, organizations can foster productive collaborations, leading to the creation of impactful data science projects that align with business objectives and resource constraints.